All right, guys, so we are now up on day 3 of solving quadratic equations. So today we're going to see kind of even more special cases. So yesterday was mostly just moving terms, right? So we saw a lot of quadratics that were not in standard form, as in they were not set equal to 0. We had to move some terms by adding opposites, and then we were able to factor them and solve them in a traditional way. So an example of that, I guess, would be number 3. Right, so we've got x squared plus x minus 20. I'd be able to factor this as the quantity x plus 5 times the quantity x minus 4. We're going to split it up and use the zero product property to set each factor equal to 0. And I'm getting a little short on space. So we've got, if we want to write it in a solution set, we've got negative 5 and we've got positive 4 as our two roots. All right, so this is a review of something I briefly touched upon on the first day, right? So we said we can factor using difference of squares, right? I would hope you would remember that. So the first one should be x plus 5, x minus 5. And we said if you're using difference of squares, that your roots of your solutions or your zeros should always be opposites. So we're always going to end up with that kind of plus minus scenario. So we get x is equal to plus or minus 5. And for this one, we did 2x plus 5, 2x minus 5. So we end up with 2x plus 5 is 0. 2x minus 5 is 0. So I'm just going to cut out some of the steps to save some space here. Right, so my first solution here, we get x is negative 5 halves. And my second one here, we get x is equal to 5 halves. So my solution would be x is equal to plus or minus 5 halves. So this is really kind of a little review of something I touched on at the end of the lesson from 2 days ago, where we were looking at just our kind of introduction into factoring, solving quadratics by factoring. So if you'd like as a now try, you can do these, right? These are pretty similar to the last ones, right? So if you want to do it, you're going to pause it now, and then we'll come back and I think just putting the roots should probably be okay here. All right, so we should have plus or minus 6, plus or minus 9, plus or minus 1, and then plus or minus 4/3. All right, so now we start to get into our special cases a little bit deeper, right? So we have 2x squared is equal to 32, so this is not in standard form. So really we'd like to set it equal to 0. See that I've got a greatest common factor. It's also not a difference of squares because 2x squared and negative 32 are not perfect squares. And that becomes pretty easy. Right, so I get x plus 4 equals 0. I get x minus 4 equals 0. So x is negative 4, x is positive 4. So I end up with x equals plus or minus 4. Now an alternative way of doing this, right? And I don't really love doing it this way just because we spend so much time kind of doing this by factoring. But if you want to kind of go back to the beginning, and if you want to do this using square roots, because we did do a lesson last week on square roots, you can actually do it that way as well. And you get plus or minus 4 that way as well. But really the best way of doing this is to do it by factoring. All right, so now we have something that is distinctly different than everything else that we've seen as far as how we're going to solve it. So we've got x squared minus 5x is equal to 0, so we have no constant. So a couple things here, right? So something we don't want to do is we don't want to divide by a variable ever. All right, if we ever divide by a variable, what's going to happen is we're going to lose one of the roots. And the root that we're going to lose is 0. So that brings us to our next kind of point. Anytime we have a quadratic equation with no constant, right? So I've got a quadratic term, I've got an x term, but I don't have a constant. One of the roots is always going to be 0, right? Because clearly if I substitute 0 for x, I'm going to get 0 minus 0 is 0. And if you divide by the variable, which again we really never do, you lose that root. Now what we're going to do instead, and this is pretty different than what we've done the last 2 days, is we're going to factor out the GCF, right? So factoring using GCF and factoring a trinomial as a product of two binomials are very different. So we're going to factor out the GCF, which is x. So it's going to look like this. Now, we still have the product of two expressions, right? Instead of, x plus 5 times x minus 2 or something like that, where we'd split it up and set each factor equal to 0, I've got x times x minus 5. It's still two factors, two quantities that are multiplied. So what I'm going to do is I can still split it up. Except one of the equations turns out to be really easy, right? The one on the right is x minus 5 can be equal to 0. But the one on the left is simply x equals 0, right? It doesn't require any more solving. It's already solved. So now I add 5 on both sides, and it gives me x is 5. So when I write my answer as a solution set, I end up with 0 and 5. And obviously if I go back and I check 0, I get 0 squared minus 0 is 0. And if I check 5, I get 5 squared minus 25 is 25 minus 25 is 0. Right, so if you don't have a constant, right, our go-to is going to be if there's no GCF, we're going to factor, or if there is a GCF, I should say, you're going to factor out the GCF. You're going to then use the zero product property to split it up. You're going to solve each equation individually. All right, so these equations look similar. They're very, very, very different. And the first one we can do in a few different ways. So one way we can do it is we can divide by 3. So that's going to give me x squared minus 9x is equal to 0. Now I divide out the GCF, which is x. Now I've got x times x minus 9. So I can say that either x is equal to 0 or x minus 9 is equal to 0. So I get x is 0 and x is 9. Now, something else we could have done, we didn't actually need to divide by 3, right? And I would always do it that way. But an alternative way of doing it is you can say, well, from the onset, the GCF is actually 3x. So you can also factor out 3x. And you can say 3x equals 0, or x minus 9 is 0. So this equation is pretty easy. The only thing is not that we have to do this, we could just say, I know that x is equal to 0, we divide by 3. So we still get the same roots. I still get 0 and I still get 9. All right, except it doesn't require you to divide. Now again, I would kind of do this. I would divide by the 3 and then factor out the x. But if you want, as an alternative, you can factor out the 3x. As long as you solve the equations and you split it up here as we should, you're going to end up with the same roots. Now we don't really have the same choices here. All right, we're going to divide by 3 because currently this is not a difference of squares, right? Because 3x squared and 27 are not perfect squares. Now it is, right? X squared minus 9. So we're going to factor this as the quantity x plus 3 times x minus 3. All right, we set them each equal to 0. And I think at this point we've done enough of these where we can determine that x is equal to plus or minus 3. But again, these two equations, right, they look very similar, but the strategies are very different and the solutions are very different, right? The only thing that's different about this second one is it doesn't have the x here. We have two different roots. Versus 0 and 9, we have plus or minus 3. So very different equations, even though they look fairly similar. All right, now everything else we're going to do for the most part are just kind of manipulations of some of the equations that we've seen. Once we factored using GCF and 5-step and product of two binomials, everything else we should be able to do. Right, so this is based on what we did yesterday, right? Putting something in standard form. And now it looks kind of like the last one where I told you that you can do it in two ways. You can factor out the real GCF, which is 7x, or we can simplify it by dividing by 7, which is what I would prefer to do. Now it becomes very simple, right? X squared minus 2x equals 0. I'm going to factor out x. So now I split it up and I get x is 0. X minus 2 is 0, so x is 2. And I'm going to write it as my solution set. X is equal to 0, or x is equal to 2. All right, so this one we could use 5-step, right? Now I told you guys with a perfect square trinomial, 5-step works perfectly fine. But really we should, at this point, I see I've got a perfect square, I see I've got a perfect square, I see the sign in the middle is negative. I should be able to factor this as a perfect square trinomial. 2x minus 5 times 2x minus 5. And we did a similar one, if not the same one, 2 days ago. So obviously I don't need to solve this equation twice. It's going to be the same equation. So I can just say 2x minus 5 equals 0. So 2x is equal to 5. So x is equal to 5 halves. Right? And again, this one is different because it's only got one solution. And the reason it has one solution is, again, it's a perfect square trinomial, meaning the factors are the same, meaning the roots are the same. So technically we say it has 2 equal roots, which is the same as just having 1 root. All right, so this is one that is completely different. Not completely different, but it's kind of integrating, I guess, everything that we've done here. So I've got a cubic. Okay, so we haven't talked about this yet. So we said that the biggest power that we see tells us how many roots you can have. So obviously in the last example, we had the second power, but we only had 1 root because it was a perfect square. That's why I say we can have. Which means I have a third degree, a third power here. I could have 3 roots. And again, that's not to say we will. And we'll do this. We'll do cubics by graphing in about a month or so. But it's possible to have 3 roots, and in this case, we will have 3 roots. So really the only way to do this is factor out the GCF. So I realize all my expressions have x. So I'm going to factor out x. So a lot of these things that we spend so much time on, right, particularly factoring completely, come into play here. This is an example of one that in order to solve it, you would have to factor completely. So hopefully we remember to factor completely. In this case, you're going to factor out the GCF, and now we're going to factor the trinomial. So this should be x plus 5 times x plus 2, and we still have the factor x outside. And now we have 3 factors. So we have 3 factors that have a product of 0. Now we're going to use the 0 product property 3 times. So the first equation is already solved for us, right? X is equal to 0. The second one, we add negative 5 on both sides. We get x is negative 5. The third one, we add negative 2 on both sides. We get x is negative 2. So now our solution set will actually have 3 distinct roots. We have negative 5, we have negative 2, and we have 0. And all of them will check. If we actually go back and sub them in individually, they're all going to end up checking our equation. All right, guys, so as always, right, so there's your now try. So if you choose to, you can work these out. So the first one, you'd have to move the 72 and divide by 2. The second one, you'd factor out the GCF of x. The third one, you can divide everything by 5 and then use difference of squares. And the last one, you'd need to move the x. Then you'd need to either divide out the 8 or factor out 8x. And if you divide out the 8, you then factor out the x, and you should be able to solve it pretty easily.